Hello and welcome to the next of these short videos about noise. This one about noise temperature. First thing, we need to revisit the concept of the maximum power theorem. You might remember that the maximum power theorem states that if we have a voltage source with a series impedance of Rs, then the maximum power we can extract into a load occurs when the resistance of the load is equal to the resistance of the source. And we can work out what that maximum power is quite easily. If we've got Vs here and Rs there and our load here, then the current flowing through the load is just Vs divided by Rs plus R load, and if Rs and R load are equal, then that's just Vs over 2 Rs. The voltage across R load is therefore, call it VL, across the load, is the current through the load, multiplied by the load resistance, which is just equal to Rs for maximum power. So, the power, which is the voltage across the load times the current through the load, is just Vs over 2 times Vs over 2 times Rs. That's just equal to Vs squared over 4 Rs. That's the maximum power we can get. Now, a voltage source in series with a resistance is exactly the model that we've been using as the noise model of a resistor. And that allows us to calculate what is the maximum power that we could extract from a resistor, just due to the fact that the resistor is noisy and has a random potential difference across its terminals due to the random motion of the electrons and the nuclei in the resistor itself. Well, the maximum power that we could extract from this is given by Vs squared over 4 Rs. And Vs squared for a noisy resistor is 4 kTbr. Divide that by 4 times Rs, that's just the value of the resistor. And the result is that the maximum power that you can get is kTb. This suggests that we can define any amount of noise in terms of the temperature of a resistor which can provide that amount of noise power. You'll notice that this is not a function of the resistance R. If we have any particular value of noise, kTb, we could just define an equivalent noise temperature given by the noise power divided by K times B. And that is what we call a noise temperature. It's the temperature of a resistor which is able to provide that amount of noise power. We can specify any noise powers in this format, and in fact it's quite commonly used for very sensitive amplifiers. They can be specified in terms of their noise temperatures rather than their noise powers. If we return to the formula that we saw in the last video for the total equivalent input noise of a series of amplifiers, that's this one. The total equivalent input noise power is the equivalent input noise of the first stage plus the equivalent input noise of the second stage divided by the gain of the first stage plus the equivalent input noise of the third stage divided by the product of the gain of the first two stages. And the formula would just continue if you have more than 3 stages. we can write this in terms of noise temperatures rather than noise powers. Just noting that these equivalent input noise powers could be expressed as K times an equivalent noise temperature times B. That would be the equivalent noise temperature of the first stage of the amplifier plus the equivalent noise temperature of the second stage of the amplifier times KB. That gives me NE2 over G1 plus KTE3 B over G1 G2. All the KBs cancel out, and we just end up with the total noise temperature of a multiple stage amplifier is the noise temperature of the first stage plus the noise temperature of the second stage divided by the gain of the first stage plus the noise temperature of the third stage divided by the gain of the first two stages, and so on if we had more stages in our amplifier. And that's really all there is to noise temperature. It's just another way of specifying an amount of noise power in terms of the temperature that a resistor would have to be at in order to give you that same amount of noise power. Next time we'll go on to talk about noise factor and noise figure, which are the final two topics in this series of videos.